Hi, so here I'm using Desmos graphing calculator, free calculator, which is pretty good, to draw the graph of a car journey. So it's quite a short journey, and the car starts from rest, and it travels. So along the x-axis, we've got a time. So that could be 1 minute and 2 minutes. So it's a 2-minute car journey. And along the y-axis, we have the distance that the car has traveled. Let's say that's 1 kilometer, that's 2 kilometers. So it takes 2 minutes to travel 2 kilometers in total on average. So it starts at rest. The car starts at rest at the starting point, and then it gradually accelerates in the first phase until it gets to the middle of the journey and its maximum speed, and then it gradually decelerates for the rest of the journey and comes to rest after 2 minutes. So the first thing, so the thing we're interested in is the kind of speed of the car during the journey. But first I'll talk a little bit about how I made this this nice curvy function. So if we look up here, that's the function itself, which is made in 2 parts. It's piecewise. It's made out of 2 pieces, the first part of the journey and the second part. First part from 0 to 1 minute is this u of x, which is this function here. So that's basically a parabola, which is sort of models constant acceleration. So the velocity is getting gradually more and more. Nice smooth function. And then for the second part, from 1 to 2, I'm using this other function here, which is also a parabola or a quadratic, but it's an inverted one, so it's slowing down, and it matches the other one kind of smoothly at the midpoint, and then it slows down and gets the maximum distance there at the peak of the parabola when the minutes equals 2, time equals 2. So hide those for a moment and show the. Okay, so this is the model of our car's journey. So it starts at rest, and it's not moving at all, and then it gradually accelerates a little bit, moves a little bit, gets a little bit faster, and so on. And then after 1 minute, it's reached a certain distance, or 1 kilometer, and then let's say it takes its foot off the accelerator and just naturally decelerates smoothly and comes to rest at the 2 kilometer mark. So if we were to measure, here's another drawing of the same journey. If we were to measure the average of the whole over the whole journey, we would have something like this, which is basically the total along the. I just made this triangle. Along the bottom, the time is 2 minutes. And along the and the distance traveled is 2 kilometers. So the average speed is the slope of this here, which is the dy over the dx. So 2 kilometers over 2 minutes. That's 1 kilometer a minute on average. So that's our average velocity. But you can see here in the middle. But you can see in the middle, the velocity is actually greatest, traveling at the fastest speed in the middle of the journey, after he's done the acceleration and before he starts slowing down, or she. And at the beginning of the journey, the speed is very slow. It's a gradual start, and at the end of the journey, the speed is very, very low. So if we wanted to sort of measure the speed. We're interested in the speed at a particular part of the journey, we'd have to move this triangle and sort of zoom in to get a better idea of the speed at a particular place. And if we zoom in, we can see this green tangent line, which matches the curve at this point here, this green tangent line. If we zoom out, we can see, okay, this green tangent line here touches the curve beautifully at this point, and this red chord line is just joining up two measurements of the function, and getting an approximate average over that period. But as we move them closer, it's going to get closer and closer to this. This red line is going to move closer and closer to this green tangent line, which is sort of what we want. And if we really zoom in, the curve looks pretty straight, and the red line, which is the average over that short period of time, giving us an average over the short period of time, is very close to the tangent line. So you can sort of see we're approximating the tangent line by taking the difference of the function. So the difference of the function is f of b minus f of a. That's dh, or the change in height. And over the bottom, we've got b minus a, which is this width across here. So we've got that height over that width is the slope of this line here. And that's going to get, and as we get smaller and smaller, in close measurement, to more precise measurement, we're going to get closer to the actual velocity. We go back to this one here. This is nice because I can just drag this around, and it's actually computing the slope at each point. So if I go here, the slope, if I go down here, we're expecting the speed to be quite slow, and the slope is kind of flat close to when we start. So we can see that the slope here is 0.4, which is quite small, and even slightly smaller there. Actually, if we zoom right in, it's going to be 0, but okay. And then as we start to speed up, the slope gets the speed gets faster, the slope gets larger, and so we can see there's 1.3, and we're at the beginning of and in the middle of the journey, when he's done most acceleration before he starts slowing down with the air resistance or the brake. That's the maximum speed we're kind of interested in, and this here is getting close to 2. And if you can see here, I've got sliders for where the point is, or I can drag it. In Desmos, you can drag it directly on the graph, which is really nice. But I can also kind of zoom in with this distance h, and get really nice and close. And if I make it small, if I make my little measurement triangle quite small, and this thing on the bottom is quite small, then I get a more accurate picture of what the actual velocity is. And so if we're really close to that midpoint, you can see down here it's going to be quite close to 0. 0.1, okay, and here it's speeding up, it's close to 1 kilometer per minute, and here it's kind of in this range here in the middle, it's kind of at a maximum velocity before he starts slowing down, or she starts slowing down. So it looks like it's getting close to 2, and if I make this even smaller, that gets closer to 2, and I can see that right there, it is actually quite close to 2. Let's have a look in the other one. Okay, if I move this one up to 1, excuse me. Okay, so we zoom in, we'll measure it here close to 1. If I put that there, you can see those are 4 units across the bottom and almost 8 units across the top, and if we move it closer, of course we're going to get, so there is an approximate, and it reads off at 1.8, and if I zoom down a bit closer, it's getting very close to 2, and if I zoom in even closer, it's getting very close to 2. So we can see that we want to know to get the instantaneous velocity, we need this nice small triangle to measure the slope over a small interval of time, so we get a really nice accurate slope. And here we're basically measuring it pretty accurately. When h is 0.03, it's a very small little triangle, so it's quite accurate. So I can just move that around and I can measure the slope at a particular point. Now, of course, this computation I can do with algebra, and the whole idea of the derivative is that I can figure out what the slope is from the function using algebra, and compute it. So we'll look at that next. Okay, so let's look at this idea of getting the slope of a function using algebra, plus this idea of that little triangle that measures the slope, and another idea of making that triangle smaller and smaller. Okay, so slope of a function. So let's have a function, some nice curve. We look at it at a couple of points, A and B, and we want to see what is f of A and what is f of B, the height of the function at those places. Okay, so here's A, here's B, here's f of A and f of B at these 2 points of interest. And if we look at this little triangle here, we've got the dy as the change in height, and the dx is the change in the base, or the time, or the x-axis. So the slope is basically this dy over this dx. How much do we, for every one that we go along, how high do we go up? And if it's a large number, then the slope is steep, and if it's a small number, then the slope is small. The slope is also called the gradient, but we'll just call it slope for ease of use. So this dy is the function at b, that's the height of that point, minus the function at a, which is the height of that point, or the height of that point there. So basically that dy is just that distance and height that we've grown. So the slope of this little triangle is a dy over dx, so it's a function of b minus a function of a. And what's a dx? A dx is just the distance between b and a, so it's b minus a. Another way we commonly write it is to use h as that distance dx. So b would be a plus h, and h would be b minus a, just the distance between them. So we can write the slope of x is approximately the function of, here we can see we're sort of renaming things. A is x is a, and h is that distance between a and b, and so b is x plus h. So another way of writing this is slope of x equals the function at x plus h, which is just b, minus the function at x, which is the same as a. So function of x plus h is that height, function of x is that height, and so we need to divide that by the distance, which is h on the bottom, and that also is the same dy over dx. Okay, so far so good. So this little triangle, okay. Here's an example. What if f of x is x squared? I mean, this general idea here works for different functions, and now I want to look at a specific one, a nice simple function, but it's not a straight line, it's a curve. So x squared is a nice simple curve that we can look at. And if we remind ourselves of the diagram of x squared, it's just a square, x times x. X squared is the area in the box. And the x plus h part will be on the side. So x plus h will be the total distance across there. H is a little bit we've added onto x to make a larger square. So the value of x plus h is that the area of that larger square with h. So it's x plus h all squared. And if we multiply that out, we get the x squared part, and we get the hx along the bottom and the hx along the side, and also this tiny little square, which is h squared. So x plus h all squared is x squared plus 2hx, that's that one and that one, plus this little bit on the corner, h squared. Okay, so f of x plus h minus f of x, which is this thing here, the dy that we want to work out, is this whole thing here. That's the f of x plus h minus f of x. But f of x is just x squared. So we notice we've got the x squared plus a bit extra plus the minus the x squared. So we're interested in this difference between this point and this point. So we take away the x squared, which is the height at a, or x. And the difference is this part here in the middle, 2hx plus h squared. But to get this s of x, we need to divide by h. So we divide that by h, and we divide that by h. And if we divide that by h, we can see an h in each part cancels out, and we have 2x, 2hx over h, which is just 2x, plus h squared over h, which is just h. So that's quite nice. So dy over dx equals 2x plus h. And this thing here, this derivative, is defined in an interesting way, that where we want to get that triangle as small as possible, ideally 0, so we're measuring it at the point, or very close to the point. So this is the way we write that. So basically this idea of limit, where h becomes smaller and smaller. We take this expression here, which we're interested in this triangle, but now we want to make excuse me, we want to make this triangle as small as possible, so we make h get smaller and smaller and smaller and smaller, and we see what happens. So we write this in the definition, the limit as h approaches 0 of this thing, dy over dx. And in our case, s of x is 2x plus h, so let's just write that in. And so we want the limit as h approaches 0 of this 2x plus h. And that is just 2x. The h gets smaller, but the 2x stays the same size. So it gets closer and closer to it. So for an example, we might have, if x was 10 and h was 0.1, so that's 10, and there's a little bit extra, 0.1, so it's quite a small triangle. At 10, we want to use to measure the gradient at 10 of x squared. And x squared, when x is 10, then x squared is 100. So this height here is 100, but then it gets a little bit larger when we move across by 0.1. So how much larger does it get? It becomes 100 plus, excuse me, that should be 100 plus 2 plus 0.1. So x of x is 2 plus 0.1 over 0.1, which equals 20 plus 0.1, which is approximately 20. And of course we could look at we could make it h smaller. We could look at 1/100th instead of 1/10th, so 0.01. Then s of x will equal 20.01. So we can see we can make this triangle as small as possible, and we're going to end up with 2x. And so we know what the derivative is at any point on this parabola x squared, and it's just 2x. So when x is 10, the derivative is 20. When x is 1, the derivative is 2, and so on and so forth.